We welcome our eminent presenter, Mr. C.M. Shylendra Kumar, Operational Unit Manager, Power Quality Products, ABB Power Products and Systems India Limited. He is an engineering graduate with over 25 years of vast experience in the field of power quality. He also holds a postgraduate diploma in systems management. He has worked with ABB India Limited and is an expert in power quality solutions and reactive power compensation. He has worked in various roles in business management, technology, quality, and product development. He has been actively participating and delivering technical papers in various national and international seminars and forums of the industry. He is a member of ET29 Committee of BIS Standards and TC33 Committee of IEC Standards. These committees are involved in framing and updating the national and international standards for capacitors, filters, and power quality solutions. Also has served as IEEMA chairman between 2008 to 2012 for the capacitor division and worked with industry colleagues, regulatory bodies, and power ministry on various issues connected with power quality.
I'm Shylendra Kumar, and I'm going to speak on power quality issues and mitigation techniques for the rail segment. Basically, the uh, agenda of this presentation is what kind of power quality issues do we face in the rail segment, especially in the metros and high-speed rail, and what is the impact of these power quality issues on the power system, and what kind of mitigation techniques are available from a supplier perspective like Hitachi Power Grids. That and when we go through these mitigation techniques, each one of these techniques, how will it solve the problem for you, and what is the techno-commercial benefits of each of these techniques when applied. That's basically the purpose of my presentation. So let me straight away go to the agenda as I've listed. I will first try to go through what is meant by power quality, a basic definition, and then what are the major power quality problems that we face in metro rail, and then what kind of power quality compensating equipment is required for metro and why is it needed. And then we go to what is known as the DRPC system, dynamic reactive compensation system, technical and commercial perspective, and how to mitigate the power quality problems and power quality offerings from ABB Power Grid company. And one case study of what we have done in Bulgarian Railways is a good case to see how we have applied the techniques and what they got from it. And another example of what we are doing in the dedicated freight for the system. So this is the agenda of today's presentation. And straight away, let me go to the introduction. What exactly do we mean by power quality? And here, if I look at it, this is a classical sine wave. When everything is good, then the sine wave is expected to be like the one at the top photo. But the power quality gets disturbed due to a lot of things that happens in the power system, especially in the railway network. Also, this is quite possible. Like we can get transients, we can have harmonics, we can have reactive power, we will have network unbalance, then we have oscillations, voltage variations, and flicker. All these things happen due to various reasons that is coming from the loads that are there in the rail system, traction being one of them. Traction is not the only reason why these disturbances come. There are a number of other loads that creates these kind of disturbances. The impact of these disturbances on the sine wave is kind of pictorially explained here, and all of these will somewhat impact the power system, the supply part of it, and also the power system, the load point of view, meaning the rail network loads itself will get impacted by these disturbances. These deviations are going to be the object of study in power quality, and then how do we rectify some of these major quality issues in the power. That's going to be the next coming slides. Now, if I take metro and high-speed rails, which is the focus area for this particular session, we are talking about a 25 kV AC power supply for the metro rail system, which is a single phase. And here we will have a lagging reactive power coming due to the traction systems, and we will have leading reactive power coming up due to unloaded cables. Now, that's one type of a problem. The other type of problems is the harmonic current that are generated by the train rectifiers and the auxiliary station loads. Then we have a huge unbalance that is coming into the picture because the trains are single phase loads basically, and then we have a lot of frequent nuisance feeder tripping also happening due to various reasons, which can also create a lot of disturbance. Then all this can create a transformer heating and insulation failure that needs to be addressed, and we have poor quality problems. Overall, if you look at it, that can affect the safety, reliability, and the whole operation system. Now, these are the causes and also some of the impacts of what happens in a 25 kV metro system, and the impact of that the waveform you can see is becoming highly distorted, and so therefore we need some correction which can be applied so that the shape of the sine wave is impact. Now, when we look at the power factor, which is the ratio of active power to the apparent power, the objective of the power quality equipment is to take the power factor to at least 0.95 or at the metering point. Then we also need to look at the harmonics generated needs to be rectified and eliminated, and also we look at unbalance that is happening in the traction system. We have to correct the unbalance. These are the things that power quality equipment needs to accomplish. Then what kind of solutions do we have when it comes to the power quality solution, especially the reactive power solutions? We traditionally used to simply apply a fixed capacitor for in parallel with load, and this fixed capacitor gave capacitive power which cancels the inductive power responsible for lagging power factor, and it used to correct the system. Then we also had CSC and TSC, which means contactor switched capacitors and thyristor switched capacitors. Now these solutions could correct the power factor when you have a varying load, but this varying, because this correction used to have step. Then the latest technology that is there is a stepless reactive power compensator, where whatever be the kind of load profile change and however fast load profile is changing, our compensator also reacts at the same speed and corrects the power factor based on whenever it is happening at whatever speed. These are the three technologies that are available to us. Let me take you through which one is best suitable for our for rail, metro, and high speed. Now, we are talking about PQCR, which is the last solution, the dynamic compensator, which is IGBT-based latest technology. We are talking that this kind of solution is the best, and the contactor switched and the TSC is not probably the best solution out of the three solutions available. Why do we say that? It's because the traction loads are highly dynamic in nature. If we look at a traction substation, we have the trains coming at a very high speed, and the load they try to remain on the system on a given TSS for a short duration and then disappear. Then there will be a lull for quite some time, and then another load comes, which means if we draw a load profile diagram, it will be highly dynamic, and the dynamic is also quite fast. So we also need a correction system for correcting the power quality issues generated by the traction, which is equally fast in reaction. This is the reason we require what we call it as PQCR, which is basically for power quality correction system, which needs to be really fast enough to react to the load, which is very fast. Then the reactive power if you take a metro, for example, it requires sometimes capacitive power and sometimes it requires inductive power, correct the reactive balance. When the traction is the main load, then we need capacitive support. And when it is a light load condition, it's only the cables that are in the picture. Then we need inductive power to be given to cancel the cable. So we sometimes require capacitive, sometimes we require inductive in order to maintain the power quality of the. So which means we need a system that can give both inductive as well as capacitive. When we talk about some traditional system, which are capacitor switched or thyristor switched capacitor solutions, they can give solution in capacitive region, but they cannot give solution in the inductive region. That is why when we talked about the latest power electronics based PQCR, as we call it, it can give correction both in the inductive side as well as the capacitive side. So now, therefore, we say that only capacitors, fixed capacitors, or for that matter, switched capacitors will not be able to solve the complete problems of what we face in metro and high-speed rail. What we therefore need is stepless, ultra-fast dynamic compensation that can work both in inductive region and the capacitive region, and that solution is the most ideal, and we call that as CR. So if we do have a capacitor-based solution, what we call it as contactor switched capacitor or thyristor switched capacitor, can give step compensation, can also have resonance issue, and therefore we say that the PQCR is probably the best suited for high-speed rail. From a technical perspective, we see what's happening in a TSS, the traction substation. We are looking at a highly dynamic load. It starts from few kVAs and goes up to several MVA within few minutes, sometimes within seconds. So we can't rely on a fixed capacitor or a fixed composition to solve the power quality problems there. The second technical perspective is that when we have traction load, when we have auxiliary AC loads and lighting, low operating power factor happens, and this can really, cause a lot of metering charges, and also, it can create a lot of power system and power issues. The maximum demand, which is also one of the electrical power bill aspect, is also going up, because when the KVR in the system goes up due to traction being inductive load and also the auxiliary loads, the total KVR demand goes up, and that really creates an issue not only on the commercial aspect, it also creates an issue that it will overload most of the power equipment that we have, because most of the power equipment is based on a certain kVA load, and if that load increases, then it means that there is overloading the system. And whenever we have the power quality issues in metro or rail system, the end result will be we have an unbalance in the voltage and we have poor voltage profile. All those impacts a lot on the life and the quality of the equipment that we have in systems. And when we correct these things, when we put a compensator and correct these things, then higher power factor will immediately reduce the KVA demand, reduces the load current, it reduces the I square R losses, and all of these are having positive benefits to rail. And not only does it give a direct benefit like this, the indirect benefit is while designing of a new station, we have a compensator factored in. It can mean that we can optimize the size of the electrical installation and not oversize it, keeping these power issues. Now, therefore, if you look at the commercial perspective of why do we need a DRPC system, a direct connection is that whenever the power factor goes down, we are talking about penalty as a loss, and when we improve the power factor, we are also talking incentive at the side. Now we have penalty for poor power factor, and we have incentive. Then the state electricity boards have been continuously increasing the target power factor, and right now they are talking about 0.98 as the target power factor. Electricity boards. Then if you look at incremental penalty, they also talk about more the power factor becomes poor, more the penalty will steeply increase. And so also it is the incentives on side. Traditionally, it was also said that lagging power factor will attract penalty. Nowadays, people have understood leading power factor means putting too much of fixed capacitor can become leading power factor during light load condition. So some SCBs have started to penalty both for lagging power factor as well as leading. So we need to correct on both the points. When there is a maximum demand exceed this, we all know traditionally that whenever we exceed the contract demand, then we end up paying penalty. That's also there. And then therefore we have penalty, and then there are some good things also that SCBs are encouraging that when we go close to unity power factor or high power factor, then we are also getting rebate the electricity bills. These are huge savings when we talk about the operating cost of high speed rails. We are calculating this on an annual basis. It comes to a very, very big sum as compared to the investment that is required on the system, dynamic system. So when we look at electricity bill, that's one aspect. The other aspect is from an O&M perspective. Operation and a maintenance person is looking at this. What does he see? He sees that there is a reduction in the KVA, therefore there is a reduction in losses, there is a reduction in heat. Therefore, he sees that the breakers, the transformer, the associated switchgear equipment, their life, their quality is improved. Poor power factor always is creating an overload of the equipment, and when the things get overloaded, the breakers are tripping, and then this leads to direct repairs. That's also a big headache for the operating guys. So therefore, when this tripping reduces and doesn't happen, then it's always a trouble-free option. And then the availability, good power factor always means that the availability of the station, and then we also look at the transformer capacity getting released because of the reduced load current. We can also connect more load to the same transformer rather than going on adding new transformers. So we are able to use the existing assets for expansion or expanded load. This is a huge thing. It avoids extension of the base. It also avoids, the extension base to be added, and we can use the existing assets. Uh, you know, Savings therefore comes from the entire system. So if you look at a metro SLD, so we have normally power coming in 66 kV or 130 kV, 20 kV, then it gets stepped down to 66%, then 25 kV, then we have an auxiliary loads running. So ideally what we do is we study the SLD like this, try to understand where the power quality issues are there, and then we apply the power quality compensators, mitigate the. So if you look at the power quality issues of the metro, what kind of solutions are we trying to provide here? We are trying to provide a dynamic reactive power compensator that works in both inductive and capacitive load. What does it do? It tries to correct the problem statement of lagging or the leading QPR. So the first problem at metro network C on a 25 kV system, we have lagging power factor coming from traction, leading power factor complex cables. This both lagging and leading KVRs are corrected by a dynamic reactive power compensator, which is very fast in correcting, and it corrects only when it is required. When it is not required, just stays at zero sometimes. The second thing is harmonics. That's the problem statement created by all the power electronics. They're in the traction system, mainly coming from drives in traction system. So the harmonic mitigator in form of active or passive compensators can give. Now this will be the correction that we give, and our solution there is taking the medium voltage PQCR. So now this is the solution that will correct the harmonics. Now, if you look at the 33 kV system, we have similarly lead and lagging KVR coming there, is coming there, various loads that are on the auxiliary system, regulators, lighting systems, escalators, interconnecting of cables, etc. So this gets corrected through a 415 volt system, which can be through a transformer. We can correct this element. And then on the 66 kV line, we have lag and lead KVR coming due to power cables, due to traction and single phase lighting ports. Now here we can give fixed inductor, a combination of active and passive. So what in nutshell I'm trying to say is that we normally study the different problem statements in a metro occurring at different voltage levels, 25 kV, 66 kV, and we apply engineered optimal power quality solutions in each of these bus levels, 25 kV bus or 33 kV bus or 66 kV bus, depending upon the situation, so that at the point of common coupling, we are having the best power quality and the least power electricity bill. So that's basically the aim of solutions. Now, if you look at I will not go through the total details of the products that we are going to use. All I'm trying to say is that we have what we know as a low voltage power quality compensator. We have a medium voltage compensator, both of which we can use based on sorry, based on the network where we are connecting it. And sometimes it is wise to connect a low voltage device to a transformer. Sometimes it's wise to use a medium voltage power compensator directly to a 25 kV system. So we have various systems that are stepless, smooth, highly dynamic in nature, like the loads itself, and they can correct reactive power, balance compensation, as well as harmonic mitigation, both at low voltage. And these are our ones. Now, if you look at the passive type of solutions, what we call it as passive harmonic, because we have expertise in this as well. This is also one of the solutions that we can apply. In some cases, we don't need electronics all the time, so we can even go for passive filters, or sometimes a combination of passive filters and active electronics. So we have both these systems coming solution. Now, if we also look at harmonic active filters, the previous slide was passive solution. Here we can have active solution, which is power electronics based, which can give any anti-harmonic, second to 50th order harmonic, cancel any harmonic by actively looking at what is there in the power system. It can give both inductive and smooth reactive. So we will have the benefits that I said earlier. So I will not repeat that. And also we can add to that the carbon dioxide emissions as well. So that we will down the power consumption and we are at CO2. We'll go through a small video that gives an example of what we have done in the case as one case study that I am presenting. And this is a 2-minute video, and let us just this is the SLD and the photo video is coming. This was this solution was applied in 5 traction substations in Bulgaria. Bulgarian Railways, who had the problems that I talked this slide, like Expo and Harmonics, and how that got corrected from 2025 dynamically. And so that is here.
Railways are one of the world's most energy-efficient means of transport. Increasing concern for the environment, rapid urbanization, volatile fuel prices, and the need to move more people and freight faster make rail a key infrastructure sector for any country. Take Bulgaria. The Bulgarian state railways are one of the oldest in Europe. They connect more than 4,200 kilometers of the country, providing passenger and freight services. This makes it a major power user. The National Railway Infrastructure Company is responsible for the smooth operation and maintenance of the country's railway infrastructure and electrical power. In broad terms, the company's electrical railway traction system comprises of large and varying loads. This demands large amounts of dynamic reactive power, which leads to low power factor and voltage fluctuations. That is poor power quality. This is harmful to the traction system itself, potentially spreading through the electrical grid and causing disruption to other users. It also incurs financial penalties on offenders. ABB designed and supplied a power electronics-based compensation solution for dynamically varying reactive power called PQC StatCon, installed in various nodes across the rail network. In simple terms, PQC StatCon is an instantaneous and stepless compensator for improving power factor and reducing voltage variations. When connected to the load, it reduces demand on the electrical network by instantaneously compensating the reactive power. Benefits include an immediate response, accurate and precise compensation without the need for manual intervention, stable voltage, a power factor that's compliant to utility standards, and the avoidance of potential penalties. With PQC StatCon and power quality monitoring equipment now installed in 5 substations across Bulgaria, National Railway Infrastructure Company expects to maintain the right power quality across its network and avoid significant financial penalties. The company will also enjoy added benefits like reliability and availability of the supply network, energy efficiency, and lower maintenance costs of its equipment. All in all, an ABB technical solution designed to benefit not just the rail company and its users, but also raise the productivity and performance of other consumers linked to the national grid. Another example of ABB's commitment to enable power and productivity for a better world.
So that was a small 2-minute video that explained, you heard the voiceover there explaining, what the benefits the customer got out of it. And so therefore, if I have to summarize, what we do is we improve the power factor and power quality, the energy efficiency, reduce the system losses. We look at reduced carbon footprint. We are dealing with reliability. We are also looking at reducing the maintenance and increasing the life of electrical installation. We're also looking at the easy way of doing installation and commissioning, and the operating the equipment. Also, we have tried to make it easy. No harmonic amplification. At the end of the day, reduced operating cost. And then for you is the availability and productivity of the electrical system that you are using. If in my last slide, I'm just giving an example of what we have done in the dedicated freight corridor. Here we are looking at WDFCC, the blue line, and the DFCC, the red line. So we are working on both these lines from a power factor, from a power quality correction perspective. And in both these places, we are giving a combination of what I said, the dynamic power compensator DRPC, combined with harmonic filters, which is capacitor based, and this hybrid system is the most optimal system that is maintaining the power factor of 0.95 and above, and also it is expected to clear the harmonics, and this way it will save a lot of electricity bill to the operators, and at the same time the rail will have very good power quality that will help the equipment themselves and also the system. So this is another example we have where we have applied power quality correction to EFCC. So this is what I have from a power quality perspective and solutions for Hitachi power grids. Thank you for your patience in listening, and that's it from my side.